much for coming along today. So we've got 4 of our master's students whose projects revolve around machine learning applications. We've formed this little, cohesive group who are going to be looking at machine learning methods and how they can be applied to build up our expertise in this area, which is like a very rapidly growing field and has lots of applications in medicine. So I'll just get them to introduce themselves when they come up and do their little bit, and please have your questions ready. We'll take them all to the end once all 4 have given their little parts. Okay, here's Nathaniel.
Okay, good afternoon everyone again, and thank you all for coming. I'm Nathaniel, and we're going to be giving you a quick presentation on this review article titled Applications and Limitations of Machine Learning in Radiation Oncology. And this will be presented by myself, Dane, Jake and Brani as part of the MPML group over in B block. So to begin, artificial intelligence is an umbrella term to describe all process aimed at imitating human intelligence. The field of machine learning falls underneath this umbrella term, and its application within radiation oncology has seen major growth within the last decade. And as shown by this figure here on the right, we can see that we are currently in a period of exponential growth of interest within this field. And often when we get exponential growth of interest over a short period of time, we get overblown expectations. And so what this paper attempts to do is address some of these overblown expectations by stating that it is important to identify 3 main components to any potential machine learning application, which are a well-defined problem, a well-defined ground truth, and a quantitative measure of correctness. And so throughout this presentation, we're going to be going through a typical external beam radiotherapy workflow. And at a majority of these steps, as you see here, we'll be introducing you to some of the current techniques that are being researched. So to begin, we have CT simulation. CT imaging only provides a snapshot of the tumour, introducing local uncertainty at the beginning of the treatment planning process. We can reduce this uncertainty by taking more images or using methods such as a 4D CT, but this will incur an additional dose to the patient, which we generally want to avoid unless we can justify it. And so current machine learning techniques seem to be going the other way, such as taking a low dose CT and reconstructing it so that it has the image quality of a routine dose CT, or taking a routine dose CT and reconstructing it so that it has the image quality of better than what we would generally expect. And there's additional research into image artifact removal. And these techniques can be applied on our usual observable images that we are used to, such as in image-to-image machine learning, or we can inject straight into the reconstruction process, such as using a scintigram as the data input before it's undergone the filtering process to become an observable image, which can potentially lead to more efficient reconstructions. And so what I've got here is a figure taken from one of the reference papers dealing with low-dose CTs. And the aim of the paper here was to take a quarter-dose CT, as you see here in the bottom left, with its low signal-to-noise ratio, and input it into a convolutional neural network and train it against the image quality of a routine dose CT. And what we get is the reconstructions we see here on the right, with these labels here indicating the slice thicknesses of the training data sets. And we can observe that the image quality seems to be at least equal to what we would expect in a routine dose CT. And we get this additional smoothing due to noise reduction as the architecture of the neural network was tailored for denoising. And so I'm just going to pass on to Dane now.
All right. Thank you, Nathaniel. So my name's Dane. I'm going to be talking about, firstly, MRI stimulation. So MRI imaging is an alternative to CT imaging, and it's quite favourable in the radiation therapy planning treatment workflow due to its non-ionizing radiation used on the patient, so there's no dose. Another attractive alternative to CT is due to its better soft tissue delineation, which is required for the improving tighter margin therapies used in today's fields. So, however, it presents the obstacle of not having access to electron density information, which is required for the calculation of the treatment plan, as we use electron density to model radiation attenuation through human tissue. So the MRI dataset actually has to be transformed into the coordinate system of the CT images. So algorithmic approaches have been developed to synthesize these CT images from MRI, such as atlas-based registration. However, machine learning approaches have also been considered. So the first type of machine learning architecture which we can use is what is called a convolutional encoder-decoder network. So this, firstly we input the MRI image into the network, and then we encode the spatial information into MRI to CT image features by narrowing and pooling the dimensions, as we can see by these alternating convolutional and down pooling layers. So once we have these MRI to CT features, we can then decode them and bring back previous high dimensional layers in an attempt to replicate the MRI image in a CT form. This type of architecture is also known as a UNet. So this has been shown to be used to some success, as shown here in a 2017 paper by Zhao Han. The proposed deep convolutional neural network method produced a mean absolute error below 85 Hounsfield units for 13 of the 18 test subjects. Basically, this just means when they compared the synthetic CT, which was generated from the MRI image, to the true ground truth CT, the difference in the pixel values was below 85 Hounsfield units. So this was significantly better than the average of 95 Hounsfield units, which was achieved with the Atlas-based method. Although training a deep convolutional neural network can be slow, training only needs to be done once. So applying a trained model to generate a completely synthetic CT volume for a new patient MRI dataset only took 9 seconds, which is much faster than the Atlas-based approach. So the second type of machine learning architecture which can be used is what is known as a generative adversarial network, a GA network. The basic components consist of a generator, which synthesizes new batches of data from scratch, and a discriminator that takes these samples from both the training data and the generator's output, and to predict whether they are real or fake. The generator, as it receives feedback from the discriminator, learns to synthesize more realistic images. The discriminator also improves over time by comparing generated samples with real samples by toggling this input here, making it harder for the generator to deceive it. So for example, say we're trying to generate completely artificial pictures of my cat. We would first begin by inputting the true ground truth real world images into the discriminator, which we would then label as a real image. We would then, by having a random input into the generator, it'll begin by creating basically rough images of what it thinks we want it to create, such as pictures of my dog, which may not be quite look like what we want to achieve. The discriminator will then recognize this as being a fake image and will, in the form of what we call loss, will give the generator feedback into how it can create a better looking image to what we desire, such as the image here. So another example of these GAN networks is shown in this study here, where they took images of a celebrity database of women with brown hair, and they required basically the generator to create completely synthetic images. And they required the discriminator to judge these images. So what this diagram here is showing is they initially started with very low resolution, low pixel images to learn the basic features which are required to create a realistic image. They then built these networks up to learn more and more complicated feature maps to eventually create quite realistic results, as you can see on the right here. And this type of building up of network is very efficient in creating quite a complex network in a short amount of time. So how does this relate to MRI simulation? So basically these GAN networks can be used to create completely synthetic CT images based off MRI images. So in a 2018 study here by Matteo and the research group, they had 91 patients who had both MRI and CT scans of the pelvic region. They divided this data into 60 and 30 images, where 60 images were used to train their very own GAN network, which could then convert these MRI images into CTs. They then, once they had the network working, they then fed the trained network the unseen 30 samples to then create their own synthetic CT images. They then applied the clinical VMAT plan the same clinical VMAT plan to both the ground truth CT and the synthetic CT to create two different dose distributions. They then compared these dose distributions using voxel-based differences, gamma analysis, and DVHs. Amazingly, the generator achieved dosimetric deviations of as little as 0.5% under realistic conditions with calculations under 30 seconds. This level of accuracy is comparable to tissue classification approaches. So as you can see here, you should be able to see here. Yeah. Well, on the left here is a dose distribution calculated based off the ground truth CT, and here is the dose distribution calculated based off the synthetic CT image, which is generated from the MRI. And here is a subtraction image showing the differences between the two dose distributions with the red hot spots and the blue cold spots. So machine learning can also be used to fuse two different modes of imaging. It's quite useful to fuse images such as PET scans and MRI images to enhance target contouring. However, it is difficult for handcrafted similarity metrics to be, one, simultaneously sophisticated enough to capture complex correlations between the two modalities, and robust enough for different tissues and noise levels to be used without significant fine-tuning. So one solution is to learn an appropriate similarity metric from training data using machine learning. As I explained before, the encoder-decoder networks can be used for this. They learn hierarchical features as a pre-processing step and have been shown to be advantageous in both computational efficiency and robustness to noise. These learned measures of similarity were found to outperform conventional metrics such as mutual information and cross-correlation, both in terms of the correctness of the metric itself as well as its effectiveness when used within the image registration workflow. However, ground truth registrations are estimates of the underlying transformations and depend on the specific protocols and algorithms used to produce them in the first place. So therefore, it's limited by the clinical correctness and realism of those examples on which the network is trained on. So now I'll be handing over to Jake, who will be talking about segmentation and contouring.
Perfect. Hi everyone, my name's Jake. I'm going to give you a brief introduction to what machine learning can be used for in the contouring segmentation field. So first of all, what is it? Well, it basically refers to the outlining of a region of interest on an acquired medical image. So it may be an organ at risk that we want to avoid, or it may be a tumour that we want to ensure we give adequate radiation to. Why would it be necessary to contour particular parts of a medical image? Well, first of all, we require precise localization of the tumours and the anatomy before we undertake any radiotherapy procedure. And also because outlining it is a prerequisite for the extraction of quantitative features from the image. So for example, if we were looking at PET images, we may want to extract the standard uptake values, either the mean or the maximum, or we would want to extract other heterogeneity quantitative parameters. So in the standard clinical workflow, the segmentation procedure is normally performed manually on a slice-by-slice basis. It's highly laborious and it's also subjective as well, which means there's high inter-observer variability. As a result, the contouring process or the segmentation process constitutes one of the largest sources of uncertainty in treatment planning. So how can machine learning help with this problem? Well, basically we can develop a model that learns to perform the same contouring task by feeding in training data, which will consist of a paired input consisting of a standard image and its manually contoured equivalent. And our model will learn to essentially replicate the process. And the best results have been achieved using what's called deep learning, specifically convolutional neural networks, which essentially just apply the repeated application of convolutional layers, which extract the salient features from the image. And this procedure has outperformed state-of-the-art algorithms in doing this. The benefits of this is that once the model is trained, the training process itself often takes very long, can even take weeks. But once you have the model, you can generate an output in seconds. So we can feed in an image that hasn't been segmented and we can achieve a segmented image in literally seconds. So this just means we have vastly decreased manual contour editing time, meaning that labour hours in the clinical workflow can be more productively spent elsewhere, which is good. But there is problems with this. So how good is our ground truth data? Well, we are comparing it to subjective clinical contours. So whilst our models will become increasingly proficient at approximating what the humans have contoured themselves, they are constrained by the accuracy of that manual segmentation. So there is essentially a ceiling on the accuracy that they can achieve depending on the quality of our input data. So our model basically can't be any more correct than the ground truth that it's designed to emulate. And we sort of run into similar problems when we consider the treatment planning aspect of the radiotherapy workflow as well. So treatment planning is essentially an optimization problem, right? We have competing objectives of wanting to minimize dose to organs at risk, and we also want to generate sufficient target coverage as well. Now, this basically requires subjective decisions on the behalf of planners most of the time. And it does present problems for machine learning algorithms to emulate because the algorithms themselves are designed to optimize a particular performance metric. So in treatment planning, it's difficult to actually quantify mathematically what the best plan would look like. So we can generally distinguish good plans from bad, but what plan would result in the best patient outcome. And as a result of this, machine learning algorithms have had trouble sort of taking off in this sphere. But it can contribute some things as well. So it can potentially reduce the planning time. It can potentially reduce the inter-operator variability and achieve a more consistent set of plans by using one model. It can also create high-quality plans very quickly, which can then be used as the baseline for manual improvements. And there has actually been some success in that. I'll hand over to Brani.
Thanks, Jake. Hello everyone, my name is Brani, and I'll be covering the QA process and how machine learning can improve QA and approval procedures in medical physics. So prior to treatment, as we know, plans must be evaluated and quality assurance measures undertaken to ensure that no errors have slipped through the treatment planning process. And standard workflows involve manual reviews and checklists that assess such things as the delineation of target volumes and organs at risk, field arrangement, collimation, target coverage, dose homogeneity, normal tissue sparing, as well as checking metrics such as normal tissue complication probability and tumor control probability charts. These procedures are very time consuming and are prone to errors as radiotherapy techniques become more complicated. And similarly, the scope of assessment becomes more complicated and prone to mistakes. And so machine learning can be injected into the workflow and automate elements of this process. It can help model relationships without being explicitly programmed and enable individualized assessment for more efficient allocation of planning resources. For example, machine learning algorithms can be trained to label anatomical structures within segmented images, serving as additional check to detect potential errors in the approval and QA process. Anomaly detection methods that are trained on a repository of correct treatments have the potential to flag outliers for human intervention when validating physical parameters such as beam configuration, monitor units, energies, and fractions. And as for checking the quality of individual plans, trained models can be used to benchmark the current plan against historical plans of similar prognosis and thereby highlighting suboptimal plan parameters. And furthermore, machine learning approaches can be taught to predict accurate gamma pass rate tests simply based off fluence maps, and thereby negating the need for very thorough evaluations, which can be time consuming. Put simply, machine learning can significantly reduce the workload of radiation oncologists and radiation therapists, as well as medical physicists, and act, in a sense, as a QA mechanism on the practitioners themselves. And machine learning in treatment delivery is another topic, and here machine learning can greatly advance the sophistication of radiation delivery by aiding in the implementation of adaptive radiotherapy. So for example, GANs, as Dane covered previously, have been used to synthesize planning CT-like images from mere CBCT acquisitions prior to a fraction. And this allows for much improved image quality and HU accuracy, which will open up the possibility of directly replanning on a CBCT and thereby implementing adaptive radiotherapy. Another application in machine learning in treatment delivery is to learn the respiration motion of individual patients. Learning methods have been shown to predict with great accuracy the location of tumors as they move due to breathing motion. This will allow for an adaptive beam realignment to occur in real time and thereby reduce the target margins and spare healthy tissues. Not all patients are suited for replanning. The extent of tumor shrinkage and anatomical changes, as well as setup variations, are the variables that are used to assess whether replanning is necessary. So a machine learning algorithm can be trained to predict the patients that would best benefit from a replanning based off a repository of previous replanning experiences. And this will, again, save resources and time for the department. And finally, the replanning itself can be automated using machine learning. This is done using a technique called reinforcement learning. So in reinforcement learning, a model navigates a synthetic model of a real system and adjusts the parameters to maximize a reward function. So in terms of radiation oncology, a model would select a sequence of learned planning decisions based off the changes in a patient anatomy. And the aim would be to maximize a given reward function. So in this case, it would be the TCP and NTCP. And then the original plan is taken as a starting point and it is adjusted to maximize the new TCP and NTCP parameters. In conclusion, this chart kind of demonstrates all of the areas that machine learning can be implemented and is currently being tested and implemented. And I think the most important thing to realize is that machine learning is only as good as the ground truth information that you feed in to train the model. So it's never going to, it's never going to exceed what you initially feed into the system. So with that being said, it's kind of used as something to help practitioners in the field and not replace them. I know there's a lot of fear going forward that everyone's going to lose their jobs, but in fact, it's just another tool, just like how the conveyor belt system helped constructing cars more easily. In the same way, machine learning can be used to aid the efficacy of treatment, get more patients through. It doesn't necessarily mean that people have to lose their jobs and whatnot. It's just another tool in the repertoire of the practitioners. Thank you, everyone.
Any questions, guys?
This one's kind of general, but do you think there's more benefit to be gained from better models or from better quality and volume of training data?
I think both go hand in hand, but of the two, the most important would be the quality of your data, because you can have the most sophisticated model, but if your training data is not good, your model is always going to be bottlenecked by that training data. And of course, if you have quality data, then better model architectures can speed up, for example, with training time. I mean, models can be trained for anywhere from 3 days to even a month, I've seen for different applications. So more efficient models can speed up training and it can improve accuracy, but definitely it's the quality of that initial data, which is the problem in the medical field, because you can't say like for example with contouring, the ground truth is it's subjective by nature. So you're always going to be you're going to be bottlenecked by that in the medical field.
Any other questions?
I have a question about the CT and MRI. So you were talking about how they try to use MRI image to basically create CT images for planning. And when you talked about this study from Matteo, what was the surname? You said the patient received a CT and an MRI image in the cohort.
Yeah.
So did they basically try to create the MRI images, the CT images from the MRI images, and use the initial CT to compare?
Yeah, that's exactly what they did.
Well they
Yeah.
okay.
So they applied the same VMAT plan to the actual CT, and then they applied that same plan to the synthetic CT, which was generated from the MRI, and they compared those two. They should be the same dose distribution essentially, but there are differences because it doesn't completely create the identical image, you know.
So they compared the two VMAT plans.
They compared, the two dose distribution
Do you know
maps.
if they also compared
Just the scans?
The CT scans?
They actually didn't know. That's what the previous study kind of did. 2 slides before, Zhao Han, using a different machine learning model. They just compared basically the pixel values, the Hounsfield units. But this one took it a step further and actually saw whether once you actually apply a map, because it should, once you kind of apply the plan, there should be even more error that comes out of it. So it kind of showed that it still holds up quite well, even after you have to apply that plan to achieve the dose distribution. Yeah. Good question.
Thank you. Got a question. So, maybe Nathaniel, if you could answer a question.
Yeah.
So, how available are the tools for doing these sorts of things, and how much effort is there from going from no knowledge about them to being able to apply them? What much effort's required there?
Well, for the tools, there's plenty of open source free software out there, such as Keras that we've used in some of the courses that we've been had to do for our course. And in terms of the level of how long it might take to understand this stuff, you can go onto YouTube and look up your neural networks, and you can already get a pretty good picture from there. There's plenty of stuff online. This is a pretty hot topic at the moment, so you don't really have to spend like massive amounts of money to do some specialized course to get this knowledge. It's basically at your fingertips.
I think the limitation is mostly the computational power, really. I mean, so for example, you could use Google Collaboratory to implement these models, but the speed of the GPU isn't really that great. So if you wanted to train a model in a short amount of time, so like Brani said, some of them can actually take months to train, depending on basically the processing power you have available. But yeah, you're sort of limited in that aspect, and a lot of the high-end GPUs cost a lot of money. So if you were willing to spend a lot of money on a really high-end GPU, you could train a model quite easily and quite quickly. And yeah, there is a lot of open source materials available, so you could pretty much jump onto Python right now and build one.
We're going to build them on our health department issued workstation.
No, probably not.
Yeah, I think it's going to take for this to be used in practice. It's going to take collaboration between computer scientists and most importantly the medical physicists and the radiation oncologists to achieve a quality that they're happy with. Because obviously these types of people don't have to know how it works, but they have to know that it's going to be working properly and there's going to be some sort of procedure in place that it's not going to have any detrimental effects and it's not going to malfunction. So I think that's probably the hardest part, is convincing everyone that it's working as it should, and it always will work as it should.
There's a lot of talk about, as Sid, that will kind of help us in our reporting of cases in the MRI and all that sort of business. But setting this all up to be as like an absolute nightmare, being sort of trying to pick a different area. So what are the practicalities of, say for example the pseudo-CT, which I can see as a great application for perhaps head and neck imaging. So we, quite often for skull base, we would do look at soft tissue areas of tumours and things, and then but also the bony detail is very, very helpful. There's probably a project in there looking at creation of pseudo CT, and does that match the quality of a high res CT that's done quite a high dose to the patient?
Yeah.
So kind of that type of thing. How because I see a lot of been to a few talks on sort of AI and all this sort of business over the years, and it seems to be a little bit of a black box. It's interesting what the comment before about learning Python, and I think I just did a course from RMIT the other week, and I could do that, and no, you don't want to do that, it's the hard way. It was 20 years later, it was 1 week and the course was short.
Yeah.
But yeah, so what are the practicalities of doing something like someone like me applying it to clinical, or developing a pipeline of analysis to get something practical? How would you do that?
What would be what could it do? How could it help you in your workflow, or what's the practicality of actually applying? Would it be hard to implement such a thing?
So if you want to analyse something, maybe a tumour in the brain or something like that,
Yeah.
You know, to me, you know, to do the deep learning